this is where the oxygen becomes important in terms of this process continuing. So without oxygen, we revert to an anaerobic pathway, and we're going to take pyruvic acid and we're going to make it become lactic acid. And what it's going to do is it's going to help at least this process of glycolysis to continue so we can produce some energy and allow, for example, exercise to continue. Now, brain activity doesn't do well, heart activity doesn't do well, okay, when it becomes incredibly deficient. But the reason we don't do well utilizing completely anaerobic metabolism is the fact that, well, how many ATP did we get out of this process? Oh, 2 net ATP, and it just can't keep up with what we need. So its product is lactic acid if we're reverting to anaerobic metabolism. Now, on the other hand, if oxygen is present, then the process continues where we're going to take pyruvic acid, and it needed to become pyruvic acid as 3 carbons to go for them to be transported from the cytoplasm into our organelle, the mitochondrion. So it gets transported as pyruvic acid into the mitochondrion. Once into the mitochondrion, we then, with an enzyme, break apart the pyruvic acid and we take off one of the carbons as well as a couple of the oxygens. Therefore, notice what's released. So as we take off the carbon and 2 oxygens, we release, as a waste product, yes we do, we release CO2. We also make more. Notice what we make. We make another NADH. Now, we actually make 2. Now, notice here it only says 1. We actually make 2. Why? Why would that be the case? Because remember up here in glycolysis, how many pyruvic acids did we make? Oh, we made 2 of them because we took C6, split it up into 2 C3s. So anything we do after that point, we're going to be doing twice. So we had 2 pyruvic acids, so we're going to get 2 CO2s, and we're going to get 2 NADHs. As we take that carbon off for CO2, notice we started with 3 carbons. Now what have we got? Yes, we do. We have 2 carbons. Well, isn't that what the coenzyme A, as the shovel, needed to throw that now as one complete molecule, acetyl coenzyme A, into Krebs cycle? So where does glycolysis occur? In the cytoplasm. Where do we form coenzyme A from pyruvic acid? In the mitochondrion. And everything we do after this point of glycolysis will occur in the mitochondrion. So be aware of that because there's very likely a test question of where does glycolysis occur? In the cytoplasm. Where does formation of coenzyme A, Krebs cycle, electron transport occur? Okay, they occur in the mitochondrion, okay, within the cytoplasm of the cell. All right, so if we kind of separate the aerobic and anaerobic. So with our anaerobic, we're taking glucose, 6 carbons, splitting up as pyruvic acid that we form as 2 3-carbon groups. If oxygen isn't present, we convert the pyruvic acid to lactic acid. But our effect is, or our result is, we get 2 net ATP. And this is just a graphic that represents them in terms of their molecular structure, not just the words. But with our aerobic respiration, now it's a little bit different, where we're going to take our 6-carbon glucose, split it up into pyruvic acid, and then within the mitochondrion, further split up into 2 2-carbon groups and release some of the CO2 that we make. Okay? And we'll do the rest here in just a minute. And those acetyl groups will be carried by coenzyme A so that they can enter into Krebs cycle. And so here's just a molecular structure, okay, our ball and stick structures representing those processes taking place. Okay, so in the next process, so this is step 3. So step 1, glycolysis. Step 2, formation of acetyl coenzyme A. Step 3, Krebs cycle. Notice that the book does a great job of reminding you what you're producing. In glycolysis, we're producing 2 net ATP and 2 NADHs. In the formation of acetyl-CoA, because we do it twice, we get 2 CO2s as well as 2 NADHs. So as coenzyme A picks up that 2-carbon acetyl group, notice it drops in the 2-carbon group and leaves. So again, it is not consumed in the reaction. It's a cofactor. It's a coenzyme in the reaction. And notice that as we drop in that 2-carbon group and it binds to the first molecule, notice what we form. There it is. We form citric acid. So why do we call it Krebs cycle? Okay, after Dr. Hans Krebs. Why do we call it the citric acid cycle? Because the first molecule formed, yes, is a 6-carbon citric acid molecule. Why is it the tricarboxylic acid cycle? Because that molecule just happens to have 3 carboxylic acid groups, okay, functional groups attached to it. So notice, and you could, again, if you take biochem class, they'll go through and teach you that starts out as citric acid and this enzyme causes this to happen and this enzyme and here's your result, and then this one causes this and this one and it works its way around. You memorize those. Yeah, we're not going to go there. But remembering, we formed 2 pyruvates, therefore we got 2 acetyl groups, therefore we're going to drop 2 acetyl groups into Krebs cycle. So anything we do here, we're going to do it twice. So kind of keep track of your yield here as we go along. So for each time through Krebs cycle, what do we make? 1, 2, 3 NADHs. What am I going to do with them? I'm going to stick them in my pocket. I'm going to save it for later. What do we also make? We're going to make 1 FADH2. But because we do this twice, we get 6 NADHs, and they're going to go right along with the ones we've already made. We're going to get 2 FADH2s, and because we do this twice, we get 2 ATPs as well. Okay. Now, as we go through this process, also notice that we're going to start, okay, we added 2 carbons into this process, so we're going to take them back away. So when it comes back around, we can add 2 more, take them away, add 2 more, take them away. So we actually, by taking off carbons, we also release 2 more CO2s as well. So that's where the last of our CO2s come off. So we release CO2 in the formation of acetyl-CoA. We also release CO2 in the process of Krebs cycle. So we put 2 in, 2 out, 2 in, 2 out. Notice how cyclic that becomes. Now here's a little bit more kind of relating. Each of the balls is representing a carbon. So as we started with this molecule, okay, oxaloacetate, so oxaloacetic acid, we had 4 carbons. We added our 2-carbon acetyl group, coenzyme A left. So acetyl-CoA comes in, drops off the 2 carbons, the CoA leaves. Now notice we had 4 plus 2 is, 6. And so as we come down, we pull off 1, now we're down to 5. We pull off another, now we're down to 4, comes back around, add 2, take away 2, add 2, take away 2. Okay? And then here's our NADHs that we make, our FADH2 that we make, as well as our ATP. But again, we go through this twice, so we get 6 total NADHs, we get 2 total FADH2s, and we get 2 ATPs out of this process.